Welcome back to the course, and let's continue our next lecture from where we have stopped our discussion. In our last class, we were talking about how to estimate the bearing capacity of the shallow foundation, and we said we have got different theories based on which we are going to be estimating the bearing capacity of our shallow foundation. And the basis for estimating the bearing capacity of the shallow foundation was derived from what is called as Prandtl's theory, where Prandtl was considering how to estimate the bearing capacity of a plate which is resting on some other metal medium. What could be the load carrying capacity of that plate he has estimated, and based on that particular Prandtl's theory, then other subsequent theories what are then derived in the aspect of shallow foundation has come into picture. So to start with, the first theory which talks about comprehensively how to evaluate or how to estimate the bearing capacity of the shallow foundation is the Terzaghi's theory, okay, which was given way back in 1943. Okay. So it need not be Terzaghi's theory or any other theories which I am going to be talking about in later stages. Do take into consideration of certain aspects which are common. What are those common aspects? Let us first understand, and then let's move into the discussion of how do we get the bearing capacity expression for estimating the load carrying capacity of our shallow foundation based on Terzaghi's theory and based on various other theories. So certain assumptions are certain things which are considered in common in any of those theories what we talk about is the estimation of the bearing capacity of that so-called shallow foundation, whatever we are going to be talking about, is for a strip footing. I repeat, it is for a strip footing. When we say strip footing, the L by B ratio of that particular footing is something greater than or equal to 10. Such kind of footing is what we call it as here strip footing. In the otherwise, this particular strip footing is what we consider as a two-dimensional problem, or the other way we also consider it as plane strain problem. So the amount of strain or the strains which are getting generated are only in two direction. That's what is called as your plane strain. In the other direction, that is in the third direction, along the length of the footing, the deformation or the subsequent strains generated are developed are considered to be zero. That's what is called as your plane strain problem. So the basic consideration in the estimation of your bearing capacity of the footings is the footing what is considered is a strip footing, and the mode of shear failure what we are going to be in common coming across was considered as general shear failure. These are certain things what we should understand. Okay, the type of footing what was considered is a strip footing, and the mode of shear failure is a general shear failure. Now, is it always that you are going to come across with a general shear failure? Why not local shear failure? Means it's not always compulsory that footing will undergo what is called a general shear failure. You might also even come across with what is called as a local shear failure. In such case, if you encounter local shear failure, then how do we modify the expressions which are given by considering what is called as general shear failure? Because the bearing capacity equations which are derived are in consideration of general shear failure criterion and in consideration of your strip footing criterion. The type of footing is a strip footing. In case if I come across with local shear failure, then I have to modify that bearing capacity equation which is given by the respective investigators. And if the footing is a circular footing, if the footing is a square footing, in case if the footing is a rectangular footing, then we should go on to modify the bearing capacity equation which is given in considering the strip footing. Okay, so bearing capacity equation what we are going to be talking about is derived in considering strip footing. But in case if I come across with any other shaped footing, then we have to modify that bearing capacity equation, and accordingly you have to use that equation for the respective footing what is given to you in your case. Okay, so let's quickly go on to understand. According to the Terzaghi's theory, as I mentioned, like Terzaghi's theory was the first theory to present a comprehensive evaluation of the ultimate bearing capacity of your rough shallow foundation. Rough in the sense the base of your foundation is rough. That's what we call it as your rough shallow foundation. According to this theory, A foundation is said to be shallow if its depth is the ratio of depth to width of the footing is less than or equal to 1. So in such consideration, Terzaghi said, okay, that so-called foundation is to be called as shallow foundation. But however, different investigators based on their studies have found that though the depth by width ratio of the footing is up to 4, if the df by b ratio of the footing is still somewhere up to 4 also, still you can consider that to be what is called as a shallow foundation. So what Terzaghi has considered, as I mentioned, the type of footing what was taken into consideration is a strip footing, or rather it is also called as a continuous footing. And taking into consideration of what is called as your general shear failure, and which has not taken when it comes to the case of your Terzaghi's theory, what he has particularly considered, I'll just try to talk in the next subsequent slide. Now, if you look at the typical case of your foundation, generally, how do we construct a foundation? You don't directly construct the foundation on the ground surface. Rather, you excavate the soil to some particular depth, and then from that particular depth, you go on to construct your so-called shallow foundation. And in such process, this is how typically your shallow foundation is going to be looking like. Let's say this is my ground surface. So at a depth of something df, below the ground surface, your foundation is constructed. Okay, so the base of the foundation is constructed at a depth of df below the ground surface. But but what Terzaghi's theory considers is the so-called depth of the soil strata df, whatever you have from the ground till the base of the footing, that df depth of the soil strata is simply replaced by what is called as a surcharge effect at the footing level. So that layer of df soil strata, the layer of soil strata of depth df, which has got some unit weight gamma. Okay, so that depth of the soil strata is simply replaced and represented in the form of what is called as your surcharge at the footing level. So in the simple form, how Terzaghi has considered now is, if this is my footing level, FL indicates footing level. So this is the footing what I am trying to look at. Okay, so all the surcharge what you were supposed to be having because of df depth of soil layer, so that depth of the effect of the depth of the soil layer is simply replaced to be indicated as what is called as surcharge at the footing level. So which I am calling it as your Q naught, or in the other way I can also call it as effective stress at the footing level is how much. So in that form it is simply replaced, and accordingly he went on to analyze how your failure surface is going to be getting developed. Okay, as like we have talked about in our previous lectures, you will first generally come across with a portion of the triangular region just immediately below the footing, which is what we are calling it as zone 1, which is considered as your what is called as your active zone, and then subsequently we are going to be coming across with what is called as your radial shear zone, and then subsequent failure surface gets extended till the footing level, which we are considering as zone 3, that is your radial shear zone, passive zone. So zone 2 is your radial shear zone, and zone 3 is what we consider as your passive zone. That's what is considered in the case of Terzaghi's theory, or in fact in all the other theories. But the difference with respect to Terzaghi's theory to that of the other theories, we'll try to understand. In the case of Terzaghi's theory, the depth of the soil strata, which extends from ground till the footing level, is simply replaced to be represented as your surcharge at the footing level. In fact, that is not the correct way of doing. Why? Because in case if the soil is not simply replaced in the form to be represented as surcharge, what would also additionally come into picture is, if I look at in this figure, if the soil is not simply replaced to be represented as your surcharge, then additional strength also gets mobilized, additional shear resistance also gets mobilized for resisting the failure in your foundation. So if additional resistance is coming into picture to prevent the failure, even over that depth of your DF layer of the soil strata, then obvious that the load carrying capacity of that particular foundation would certainly go little more higher, as we are taking into consideration of your shear strength, what is getting mobilized or resisted over that depth of your DF layer of the soil strata, which is not taken into consideration in your Terzaghi's theory. In case if that was also taken into consideration, then your estimation for bearing capacity would certainly come out to be relatively higher. The value of your estimated bearing capacity would certainly come out to be higher because of the shear strength parameters of the soil, which are also duly taken into consideration over the depth of your DF layer of the soil strata, which is varying from the ground surface to that of your footing level. That is something what Terzaghi has not considered. And according to the Terzaghi's theory, if you try to look at, let me erase all this. Yeah. According to the Terzaghi's theory, what he has seen is, in this triangular wedge region, that is in the active zone region, this so-called failure surface, this AD line and AC line are nothing but we call it as your failure surface corresponding to your active zone. So that failure surface is existing at an inclination of what is called as phi, which is otherwise also called as your angle of shearing resistance value of that particular soil. And your passive zone, in the case of your passive zone, that so-called failure surface, what we are trying to define for that passive zone is considered to be existing at an inclination of 45 minus 5/2 with the horizontal. That comes from your basic fundamentals of your Mohr circle concept, where we are in the other way, like from your earth pressure, when we have talked about, we have understood in the case of active state, the failure surface exists at an angle of inclination so and so with the horizontal, 45 plus 5/2 with the horizontal. In the case of passive state, your failure surface gets developed at an angle of inclination 45 minus 5/2 with the horizontal. So from that basic fundamentals only, we are trying to represent for your passive zone as 45 minus 5/2 with the horizontal. But in the case of active zone, Terzaghi considered that the failure surface would get developed at an inclination of 5 with the horizontal. Whereas when it comes to the case of the other subsequent theories, we do come across with the situation like in the case of active zone, the failure surface generally do not get developed at an inclination of 5 with the horizontal. Rather, it is taken into consideration as 45 plus 5/2 in the case of your active zone, which we have learned from your earth pressure concept according to Rankine's earth pressure theory. Okay. So which will look in the other theories, but in the case of Terzaghi's theory, so we see in the case of active zone, the failure surface is considered to be getting developed at an inclination of 5 with the horizontal, and in the passive zone, it is 45 minus 5/2. And what we are going to be ultimately understanding in this Terzaghi's theory is how the bearing capacity equation, the so-called bearing capacity equation, is derived. Okay, and what is the basis for deriving that particular bearing capacity equation? So this is typically how your failure surface is getting generated. This your wedge zone, which we are calling it as your active zone, and this region of the radial shear zone is zone 2, and this is your third zone. That is what we are calling it as your passive zone. So whatever we have been talking about are in detail represented with respect to this particular picture. What does each of that region going from 1 to 1, how that angle is represented is explained in this particular slides. Okay. You can quickly go through those statements. The angles, what I have talked about, what is being represented with respect to which surface that angles are defined, everything is represented there. Now, how we are going to be estimating that so-called load carrying capacity of that foundation according to your Terzaghi's theory. So what we try to look at here is, in order to say my foundation is safe just before at the verge of the failure, what is the maximum load that your foundation is capable of carrying onto it? So if I want to find out, so I'll try to do that based on what is called as your equilibrium, and I am going to analyze this particular equilibrium of the wedge. That's the soil wedge which you have in the region immediately below your foundation. So we'll be looking at the soil wedge. That's nothing but your soil corresponding to your active zone. We'll look at the forces acting on that particular wedge, and we go on to apply the equilibrium conditions. That's net summation of forces acting on that particular soil wedge. In the horizontal direction, we equate it to 0. In the vertical direction, we equate it to 0, to go on to find out what is called as your load carrying capacity, ultimate load carrying capacity of your foundation. Okay, so we simplify this forces acting on this particular soil wedge, both in vertical and horizontal direction, and we go on to derive this particular expression from there. Okay, and the generalized expression, what we are going to be deriving from the equilibrium conditions, because I'm not writing down the equilibrium conditions here, and we are not going on to derive that. So anyone who is interested can refer to any of the standard textbooks that we have referred in our course. It could be your BM Das, or even your Gopal Ranjan, or foundation analysis by Lamb and Whitman. Any of those books you can refer to get that expression, like how the equilibrium equations are applied and how we are getting that generalized expression for estimating the ultimate bearing capacity. So the generalized expression, what we are going to be getting after applying the equilibrium equations is QU. QU refers to that of your ultimate bearing capacity of the footing, which is equal to CNC plus QNQ plus half gamma B n gamma. I'll tell you what does each of the term refers to, and how we are going to have the changes in this particular expression in taking into consideration of the different shapes of the footing and different properties of the soil. Like, as I said, we are considering blindly that a general shear mode of failure will happen, but it may not be always that general shear failure takes place. You might also even come across with local shear failure. We don't generally come across with what is called as punching shear failure in the case of shallow foundation, because if the soil is soft or the soil is loose, we don't generally prefer to go for what is called as shallow foundation there. In such kind of soil deposits, we prefer to go for what is called as a deep foundation. So in such case, you don't expect to have what is called as a punching shear failure to typically happen in the case of a shallow foundation. Okay, so in this particular generalized expression, whatever we are talking about, irrespective of which theory you are referring to, the generalized expression is going to be this. So do remember this particular expression for ultimate bearing capacity, which is given in a generalized form. Okay, this I can write it as the generalized equation for estimation of bearing capacity of footing. Now, in this particular expression, if you look at in the first term, if I see, what does C refers to? C refers to the cohesion value of the soil, the cohesion value of the soil on which the foundation is resting, and NC, NQ in the second term, N gamma in the third term. NC, NQ, N gamma, those three terms are those three parameters what we have represented are nothing but they are called as your bearing capacity factors. NC, NQ, N gamma are nothing but they are called as bearing capacity factors. Term C refers to that of the cohesion value of the soil on which the footing is resting, and Q refers to that of the amount of surcharge stress or the effective stress which you are simply replacing the depth of the soil strata to indicate that surcharge stress at the footing level. And in the third term, gamma refers to that of the unit weight of the soil which is there below the footing, and B refers to that of the width of the footing. Okay, width of that particular shallow footing what we are talking about. And this is a generalized expression. As I mentioned, like in case if you have different shape of the footings, okay, so it need not be always a strip footing, it could be any other shaped footing. Then what we do is we correct that bearing capacity expression, whatever generalized expression we have, we go on to correct that bearing capacity expression. So how do we correct that bearing capacity expression? What we do is we multiply each of those terms. We have three terms, CNC, Q and Q, half gamma, B and gamma. These three terms are going to be multiplied with their respective shape correction factors. In case if the shape of the footing is rectangular or square or circular, then we multiply each of those terms what we have in the generalized expression with what is called as shape correction factor. And always you may not represent your footing at the ground surface. Okay. It might be embedded into some deeper depths into the ground. So in such case, we go on to apply what is called as depth correction factor for each of the term mentioned in the generalized expression. And as I mentioned, you may not always have general shear failure, general shear mode of failure. So you might also even encounter sometimes local shear mode of failure. So we go on to modify your three terms by applying certain corrections for your C5 values of that particular soil. And it may not be always that you will have only vertical load which is passing through the CG of the footing. Sometimes you might also even come across with some inclined loads what your footing is subjected to. So in such case of inclined forces acting on the footing, then we go on to apply the correction for your bearing capacity equation, like multiplying with what is called as inclination correction factors for each of your terms in that generalized bearing capacity equation. And likewise, you have various other corrections that we also come across with, depending on the case that we are dealing with. One more example, like always the load may not be passing through the CG of the footing. Let's say the load is vertical, but it may not be always passing through the CG of the footing. So you might have some eccentricity in your loading, which is passing through the footing. So in such case, due to that effect of eccentricity, there should be some correction that is to be applied for your bearing capacity expression, what you have generalized and represented. And always you may not have a situation where the base of the footing is horizontal. So sometimes the base of the footing could be inclined. So we go on to apply what is called as base correction for your bearing capacity equation. And sometimes you may, there may not be always a situation where the ground surface is horizontal. So ground surface could be sometimes also inclined. So in such case, if the ground surface is inclined, the effect of that inclination of the ground surface will also be taken into consideration in modifying your bearing capacity equation, generalized bearing capacity equation. So what I just mean to say is the expression what we have represented here, CNC plus QNQ plus half gamma BN gamma, is a generalized expression. Now, depending on the criteria that you are dealing with, we are going to be modifying that particular generalized expression according to the requirement of your problem what you are dealing with. Okay. So as I mentioned, like in case if we are dealing with any other shape of the footing apart from your what is called as your strip footing, if you are encountering with any other shape of the footing, it could be a rectangular footing or a square footing or circular footing. So what we do is all those three respective terms are going to be multiplied with their respective correction factor. Which correction? Correction for shape I am talking about. So here SC, SQ, S gamma are nothing but we call them as your shape correction factors. So why I am applying the correction for shape? Because the footing that I am dealing with may not be what is called as your strip footing. In case if it is any other, then I have to multiply each of those three terms that I have in my bearing capacity expression. So each of those terms are going to be multiplied with respect to their shape correction factors. Okay. So SC is the shape correction factor what I should multiply to your cohesion term. If you can see, this is the term associated to cohesion parameter, and this is the term which is associated to what is called as surcharge parameter, and this is the term what is corresponding to your unit weight parameter. That's how I remember them, and I go on to multiply those respective correction factors, which makes my life so simple in understanding them, which term is to be multiplied to what. So if I say this is my cohesion term, then corresponding shape correction factor, I'll indicate it as SC. If I consider it as my surcharge term, then corresponding shape correction factor, I'll be multiplying it as SQ. And if I remember this in terms of the unit weight term, then the corresponding shape correction factor, I'll be multiplying it as S gamma. Okay. So as I mentioned in our earlier slide, So what does each of the term in the expression refers to? B indicates the width of the footing. In case if it is a circular footing, the width of the footing what you are supposed to be substituting is nothing but the diameter of the footing. And gamma indicates in the expression what we have here in this particular expression, gamma refers to the unit weight of the soil which is there below the foundation level. And Q indicates what is called as surcharge. This is nothing but it refers to that of the soil which is there above the footing level. So here in this particular expression of surcharge, when you look at the term gamma, this gamma refers to that of the unit weight of the soil which is there above the footing level. Why I am specifically talking about this is, always you may not have the soil which is uniform above the footing and below the footing. Sometimes below the footing you might have some different condition of the soil, above the footing you might have different condition of the soil. So you have to be little careful while talking about that particular surcharge term and the unit weight term which relates to that of the soil which is there below the footing and above the footing. As I mentioned, like NC, NQ, N gamma parameters are nothing but we call them as your bearing capacity factors. So we have different expressions for estimating this bearing capacity factors according to the different theories that we come across with. And SC, SQ, S gamma, they are nothing but we call them as your shape correction factors, taking into consideration of the different shapes of the footings. According to Das 4.1, table 4.1 of your BM Das test book for foundation analysis book. Okay. So from that, if we refer to for phi value is equal to 0, we have NC, NQ, N gamma values. These are standard values, so which everyone is expected to remember. Okay, so NC is what you will be getting it as 5.71, NQ is what you will be getting it as 1, and N gamma is what we will be indicating it as 0. These values are standard for phi value is equal to 0. If the soil has got phi value equal to 0, then the NC, NQ, N gamma corresponding parameters are 5.7, 1 and 0. In case if your phi value is not equal to 0, then those bearing capacity factors, according to Terzaghi's theory, the bearing capacity factors NC, NQ, N gamma are given like this. The expression for NC is given as cot phi dash into NQ minus 1, where the expression for NQ is given as e to the power of 3 pi by 2 minus phi dash into tan phi dash divided by 2 into cos square pi by 4 plus phi dash by 2. This is the expression what we have for NQ term, for calculating what will be your NQ term. And similarly, N gamma is what is given as half into Kp by cos square phi or cos square phi dash minus 1 into tan phi dash. Okay, this is the expression for NC, this is the expression for NQ, and this is the expression for N gamma. So if I know what is my NQ, I can subsequently go on to calculate NC, and I can also calculate what is N gamma. In this particular expressions, if you look at, NQ term, when you are calculating, you have to be little careful because the value NQ expression is given as e to the power of 3 pi by 2 minus phi dash. Here the phi dash value what you should be substituting is in terms of radians. So you have to be little careful. So when you are substituting phi dash in radians, then if at all a phi dash value, if you know in terms of angle, then that angle into pi by 180 you have to multiply to get what is your phi dash in terms of the radians here. And tan of phi dash when you are substituting, then there phi dash value is going to be substituted in terms of your degrees only, right? So in N gamma parameter, if you look at Kp here refers to that of your passive earth pressure coefficient. Okay, so here I am indicating where Kp is nothing but we call it as your passive earth pressure coefficient. We know how to calculate your passive earth pressure coefficient, which we have already seen, which I can write it as 1 plus sine phi dash by 1 minus sine pi dash, or otherwise I can also represent it as tan square pi by 4 plus pi dash by 2. So in either of the way, you can go on to represent your Kp parameter. And once I know what is my phi dash value of the soil, I can calculate my Kp. Then I can go on to substitute in n gamma expression to get your n gamma parameter. So for any other phi values apart from phi is equal to 0, as I said, phi if it is equal to 0, according to Terzaghi's theory, the NC, NQ, N gamma parameters are some standard values which we have seen in our previous slide. Like NC is 5.7, N gamma, NQ is 1, and N gamma is equal to 0. But in case for any other phi value, so for phi value greater than 0, if I am trying to look at, then these are the set of expressions which you can make use of to calculate your NC, NQ, and subsequently N gamma parameters. If you look at any of the standard textbooks, you might find some standard curves or tables which are defining what are your NC, NQ, N gamma parameters for different phi values. So you can, let's say for phi is equal to 5 degrees or 10 degrees or something 15, you can directly look at the table and pick what are your NC, NQ, N gamma parameters, and you can make use of in your calculation of the ultimate bearing capacity of that particular footing according to the Terzaghi's theory. Yeah. So in this particular expression, as I mentioned, SC, SQ, S gamma are nothing but they are indicating you what is called as your shape correction factors, and the expression for those shape correction factors are the values of those shape correction factors are indicated in this particular table as per Terzaghi's theory. So those shape correction factors are given like this. The shape, in case if the type of footing is a square footing, then SC value is going to be 1.3, SQ value is going to be 1, S gamma value, what you are supposed to be substituting in the expression, is 0.8. If it is a circular footing, then SC, SQ, S gamma, accordingly you will be substituting. In case if it is a rectangular footing, then your SC is what will substitute as 1 plus 0.3 into B by L, SQ is 1, S gamma is nothing but 1 minus 0.2 into B by L. So according to the dimensions of that particular footing, if you know what is the length of that rectangular footing, width of the rectangular footing, then you can go on to substitute into that shape correction factor terms, expressions, and you will be getting the values of those respective shape correction factors for that typical type of rectangular shape footing. And once you know those corresponding shape correction factor, you can go on to multiply into that expression to get what is the ultimate bearing capacity of that particular footing, taking into consideration of the effect of different shape also. And as mentioned, like always, you may not encounter what is called as your general shear mode of failure happening in your soil. So you might also even come across with what is called as local shear failure criterion. In case if it is a local shear failure criterion, because of which the foundation is undergoing the failure, then what we do is we modify what is called as the cohesion parameter in the generalized form of your ultimate bearing capacity. If you look at in our earlier expression, we said it's nothing but CNC plus QNQ plus half gamma BN gamma. Okay, and the generalized form of that expression, the cohesion term and your unit weight term, what you are going to be having, or rather I should not call it as unit weight term, the cohesion term and the angle of shearing resistance term, those terms are going to be modified. I repeat, we are going to be modifying the cohesion term and your angle of shearing resistance term, and by modifying that cohesion and angle of shearing resistance term, then we are going to be accordingly going back to substitute into the expression of your generalized equation of the bearing capacity, and accordingly we are going to be calculating it. Okay, so if phi value is the phi value is modified, this here phi dash indicates the modified phi value, or sometimes it can also be indicated as phi n. Okay, so once the phi value is modified, then automatically the subsequent NC, NQ, N gamma parameters what you are going to be calculating should be calculated based on your modified phi value. Okay, so please do take into consideration. And the C value what you are going to be substituting in the bearing capacity equation, the C should not be the original C value of that soil as it is. You have to modify that C value and accordingly make use of that particular modified C value which is to be substituted into this bearing capacity equation. Why are we modifying the C and phi parameters? Means because the generalized expression for estimating the bearing capacity was derived in considering the general shear failure. If it is general shear failure, the generalized form of the expression was very much valid. But if it is not the general shear failure, if it is a local shear failure, what you are coming across with, then the corresponding C5 parameters of the soil shall not be directly incorporated into your bearing capacity equation. They are to be accordingly modified, and we should go on to substitute into the original form of your bearing capacity equation, what is given. Okay. So these are your modified cohesion and modified surcharge, modified angle of shearing resistance terms. That's how you go on to calculate. And next, moving ahead, this effect of local shear failure, how we are correcting your C and phi parameters, is valid across all the theories. It's not particular to that of your Terzaghi's theory only. So it's valid across all the theories. In any of the theory, when you are estimating the bearing capacity of the footing or bearing capacity of the foundation, where you see the condition of what is called as local shear failure. Sir, how do I know it's a local shear failure happening in the soil? So in the problem, if you look at your C and phi value, if it is greater than, less than 29 degrees, it indicates that you are going to have what is called as a local shear failure in that particular soil. If the phi value is greater than 36 degrees, it clearly indicates it's a general shear failure. If it is in between 29 to 36 degrees, as we said, we are going to estimate the ultimate bearing capacity based on an interpolation technique, considering the mode of shear failure, something in between local shear to general shear failure. Not particularly local shear failure, not particularly general shear failure. So moving on to Mayerhof's theory for estimating. Earlier we were trying to talk about Terzaghi's theory. Based on Terzaghi's theory, how the bearing capacity expression is derived and how do we go on to estimate your bearing capacity of that particular footing according to Terzaghi's theory. And let's now quickly understand, according to Mayerhof's theory, how we are going to estimate the bearing capacity of your shallow foundation. As I said, in the case of Terzaghi's theory, we had a drawback. What is that particular major drawback? In the sense, the depth of the soil strata df is simply replaced in the form of what is called as surcharge at the footing level. Okay. Because of that replacement of the depth of the soil strata as surcharge at the footing level, what is happening or what is that we are missing is the strength characteristics of the soil over a depth of df are not taken into consideration, because of which the estimated bearing capacity according to Terzaghi's theory is not that much appropriate or accurate. Now, coming to the case of Mayerhof's theory, what he has additionally considered here, apart from typical Terzaghi's theory, what additionally Mayerhof has also looked in is he has also taken into consideration of the effect of the shear strength parameters of the soil over the depth of the soil strata. By taking that into consideration, what is going to happen is your passive zone failure surface is not going to be represented only till your footing surface. The so-called passive zone, earlier in our previous slides, we were representing our passive zone failure surface only till the ground. Only till the footing level. But to be very particular about that, so-called failure surface will not develop only till the footing level, rather it gets extended till the ground surface. In the process, if it has to get extended till the ground surface, then the amount of load what is to be transferred through the footing is going to be relatively something higher, because this much depth of the soil strata, df depth of the soil strata, would offer some resistance against the failure. Okay. Additional resistance will be generated, or additional resistance would be getting developed against the failure, which is even supposed to be getting extended over the depth of your df layer of the soil strata. So that's an additional parameter what Mayerhof has taken into consideration, and according to that he went on to derive the expression for ultimate bearing capacity of that particular footing. As I mentioned, any theory, it doesn't matter. The generalized form of your ultimate bearing capacity of the footing is the same, that is CNC plus QNQ plus half gamma B N gamma. What varies is the corresponding bearing capacity factors would vary, because from one theory to the other theory, the approach by which you are estimating your ultimate bearing capacity of the footing is changing. So obvious that the corresponding parameters what are involved in that generalized form of the bearing capacity would get modified. So your NC, NQ, N gamma parameters, that's your bearing capacity factors what you have. According to Mayerhof, they are going to be different from that of what you have for your Terzaghi. Okay. So this indicates that the failure surface is even considered to get extended over the depth of the soil strata dl. On the other side, only I am talking about this failure surface indicated on the right side of the footing. So it doesn't mean only failure gets generated only towards the right side of the footing. In similar way, in the symmetric fashion, you will be having on this side also the failure surface getting developed in a symmetric pattern on the other side also. The same thing is discussed, indicated in this particular slide. Okay, so the generalized form of your bearing capacity, what we'll be once again getting is Q ultimate is equal to CNC plus QNQ plus half gamma B N gamma. And NC, NQ, N gamma parameters, as I said, they are nothing but your bearing capacity factors. We'll see what are those expressions for estimating NC, NQ, N gamma parameters in the next subsequent slide. In case if the type of footing what I am talking about is not a strip footing, if it is what is called as your square footing or rectangular footing or circular footing, then what we do is we go on to multiply with its respective shape correction factor. Let's say the footing is not at the ground surface. If it is embedded to some depth below the ground surface, then in addition to this shape correction factors if required, let's say my footing, the problem statement is like this. Footing is a rectangular footing which is embedded at a depth of 2 meters below the ground surface, and you have what is called as an inclined load coming from your superstructure through the footing onto your ground. Okay, so there are various factors now that I should take into consideration. Okay, my footing is a rectangular footing, then I should multiply what is called as your shape correction factors. Footing is embedded at some depth below the ground surface, then depth correction factors are also to be taken into consideration. And type of load what is coming is not a vertical load, rather it is an inclined load. Then inclination correction factors also I should be talking about. So in such kind of problems where you have multiple things that are to be corrected for, then your bearing capacity expression, I would say you write your bearing capacity expression like this: CNC plus QNQ plus half gamma B N gamma. Now, depending on what is given in your problem, okay, my footing, what is given in the problem is shape, is a rectangular footing. Then multiply with the corresponding shape correction factors, SC, SQ, S gamma. What are your SC, SQ, S gamma expressions according to Mayerhof's theory? Okay, we can look at any of the standard book. Okay, SC, SQ, S gamma expressions I can calculate based on this set of equations what are given by Mayerhof or what are given by Terzaghi or what are given by any other person like Vesic or Hansen or Skempton or whatever, whoever it is. So I can look at that set of expressions and I can go on to substitute in the place of SC, SQ, S gamma, and I can multiply to your generalized form of your bearing capacity expression. And as I said in the problem, it's a rectangular footing which is embedded at a depth of 2 meters. So if it is embedded at a depth of 2 meters, then your depth correction factor should also be taken into consideration. Why? Because over the depth of 2 meters, there is an additional resistance what is getting developed against the failure surface. So the depth correction factor should also be looked at, which is not taken into consideration according to your Terzaghi's theory. So depth correction factor is DC, DQ, and D gamma. For their respective terms, I should be multiplying. And as I said, the load is not a vertical load, rather it is an inclined load. Then your bearing capacity terms should also be corrected for what is called as your inclination correction factors. Now, let's say if your footing, the base of the footing, this particular base of the footing, what we are talking about is generally the footing was supposed to be constructed like this. But instead of this way, if the footing was constructed like this, the base of the footing was constructed with some inclination. Let's say some eta is the inclination. So then subsequently the bearing capacity what you are going to be estimating should also have this effect of that inclination of the base. Then in such case we go on to multiply your cohesion term, surcharge term and unit weight term with what is called as your base correction factors also, which I'll write it as BC, BQ into B gamma. And likewise, as I mentioned, if the ground is, generally we consider ground to be horizontal, but instead if the ground is not horizontal, if the ground is something sloping like this, where the inclination of this ground is beta, in this particular, if you are constructing a foundation, then the effect of surcharge on either side of the footing is not uniform. Then we go on to multiply with what is called as your ground correction factors. So likewise, you have different correction factors which we come across with. We'll also come across with what is called as water table correction factor. Why water table correction factor? Depending on the position of the water table, if it is very far away from the bottom of your footing, if it is just below the footing, if it is above the footing, then obvious that the so-called shear strength aspects of the soil would get changed. So water table correction is to be taken into consideration. If the loading has got some eccentricity, if the axis of the loading is not passing through the axis of the footing, then you have some eccentricity correction that is to be applied. So depending on what is to be dealt with in that particular problem, you have to multiply their respective correction factor terms to your cohesion, all your three individual terms that you have in your generalized form of the bearing capacity equation. That is your cohesion terms, surcharge term and your unit weight terms. Okay, so depending on what type of correction that is to be applied to your general form of the expression, so you go on to apply that respective correction and then we can go on to calculate your ultimate bearing capacity of the footing. Okay, so this will little more clearly we'll be understanding as we go on to solve the problems, because how that correction factors are to be applied for that problem, which corrections are to be applied for that problem and all, we'll try to more clearly understand as we go on by solving some problems. These are the set of bearing capacity factor expressions for NC, NQ and N gamma according to Mayerhof's theory. And according to Mayerhof, for phi is equal to 0, the respective NC, NQ, N gamma values, what we are going to have is NC is 5.14, NQ is 1, N gamma is 0. Please, this is also standard value you are required to remember. So for any other 5 greater than 0, then you can make use of this set of bearing capacity equations what you have, and you can go on to solve for NC, NQ, N gamma values, and you can substitute into your bearing capacity equation. And if you look at any of your standard books, this you'll find the standard tables or standard charts even for estimating your NC, NQ, N gamma values from your known phi parameter that you have for that particular soil. And these are your set of shape correction factors what we have according to Mayerhof's theory. So the corresponding shape correction factor is how much for cohesion term, surcharge term and unit weight term. So you can go on to make use of these expressions to calculate SC, SQ, S gamma parameters. And depth correction factors, depending on what is the depth of your foundation. So you can make use of this set of expressions to calculate your depth correction factors also. So depending on the data what we are dealing with in that problem, where we are estimating the bearing capacity of that footing, we'll understand whether I have only shape correction factor, whether I have shape correction factor and depth correction factor, whether I have only depth correction factor, whether I have only inclination correction factor. So it all depends on the problem that we are dealing with, the type of footing that we are dealing with. These are your inclination correction factors, which are given by Mayerhof, where if you look at here in this expression, theta indicates the angle made by the resultant force. I repeat, the angle made by the resultant force. Resultant force means it's your inclined force. The angle made by your resultant force, otherwise also called as your inclined force, with the vertical. So that angle is what is indicated as theta. And moving on to the Hansen's theory, based on which we are going to be talking about how to estimate the bearing capacity of the footing. See, Hansen's theory and Mayerhof's theory, these two theories are more widely used in the estimation of bearing capacity of the footing because of their simplicity in estimating the bearing capacity of the footing. So Mayerhof theory is something more commonly used, but however, depending on the type of soil, even this Mayerhof's theory and Hansen's theory are other theories also. Like in some kind of soils, in some type of conditions, the values estimated based on those theories are very conservative. They are much higher than that of what the original value it should have been, or it should the values what were calculated might have been less than that of what should have been for that original footing. Okay, so exact values will be able to get only when you conduct some field test on that particular footing to get how exact what is going to be your ultimate bearing capacity of the footing. But what we are talking here is theoretical. By theoretical approach, how do we estimate the bearing capacity of that shallow foundation based on different theories? It is what we are trying to talk about. Why? Because why are we talking about this theoretical approaches? It's not possible always to go to the field, construct that typical shallow foundation, and then go on to conduct your field test on that original type of shallow foundation. Okay, so in order to avoid that, we depend on different theoretical approaches, which is more suitable for what type of soil condition. Then depending on the suitability of that soil condition, there are certain theories which are more appropriate. Like Hansen's bearing capacity equation is more realistic in estimating the bearing capacity of foundations embedded in cohesive soil deposits. Okay, whereas the same Hansen's bearing capacity equation is found to be conservative in the case of your cohesionless soil deposits. Okay, so some certain theories are more effective pertaining to some particular type of soil condition. So in addition to what we have learned in Mayerhof's theory, Terzaghi's theory, we started understanding that Terzaghi has not taken into consideration of the soil properties or the effect of shear failure happening in the depth of DF layer of the soil strata, which Mayerhof has taken into consideration. In addition to that, what is considered by Mayerhof, Hansen went on to even consider some other additional parameters like the inclination of the base of the footing. That means if the base of the footing is not horizontal, not resting on a horizontal surface, it's resting on some inclined surface. Or if the ground surface is not horizontal, if the ground surface is inclined. So such effects are also even additionally taken into consideration by Hansen in estimating the bearing capacity of your foundation. So Hansen's bearing capacity, if I am trying to talk about, so Hansen talks about considering the effect of shape, effect of depth, effect of inclination, effect of your ground inclination, effect of your base inclination, and it also takes into consideration of your effect of eccentricity. So whenever your eccentricity effect is taken into consideration, there we go on to modify the dimensions of your footing. That I'll try to talk in the next subsequent class, where we'll try to understand how your geometry of the footing is modified because of your eccentricity effect, or taking into consideration of your eccentricity correction for that footing because of that eccentric loading criteria. So how do we modify your bearing capacity expression? Which terms are to be modified? We'll try to see, and accordingly we'll understand how to estimate the ultimate bearing capacity of the footing. Then according to Hansen's theory, the bearing capacity factors NC, NQ, and gamma is what we can calculate from this set of expressions. and for phi is equal to 0, the respective NC, NQ, N gamma according to Hansen's theory is 5.141 and 0. And likewise, you have set of shape correction factors which are given by Hansen. And we have got the depth correction factors which are given by Hansen. Based on these equations, we can go on to solve for your depth correction factors according to Hansen. And you have to be little careful, like which set of expression is valid for what condition is very clearly indicated. If you can look at here, so this so-called K parameter, what you are going to be substituting into this expression. So K is represented as the ratio of dF by B in the case if that ratio of dF by B is less than or equal to 1, where this K is given as tan inverse of dF by B if the dF by B ratio is greater than 1. So you have to be little careful. And this set of expressions, what I am trying to talk about, are in considering your phi value of the soil, which is equal to, for phi value of the soil, which is greater than 0. In case if the phi value of the soil, if it is equal to 0, we have the ultimate bearing capacity expression given in a simplified form, and there you have got other set of expressions which are to be used for estimating your correction factors. These are your inclination correction factor expressions. Okay, we can make use of these inclination correction factor expressions depending on the condition what we are looking at. And these set are the ground correction factor expressions according to Hansen. And these set of equations are your base correction factors according to Hansen. And as I mentioned, like in case if the soil is like if the soil has got phi value is equal to 0, then your if phi is equal to 0, automatically what we say is that your according to Hansen, only NC parameter exists, that is nothing but 5.14, whereas your NQ is nothing but it is equal to 1 and N gamma is nothing but it is equal to 0. Okay, so N gamma term will vanish, and as NQ is equal to 1, then that corresponding NQ value is replaced as 1 for your QNQ term, and for your first, that's your cohesion term, you have your respective correction factors which are to be accordingly applied depending on what all correction factors that are to be considered. If it is depth correction factor, then we do take into consideration of depth correction. If it is inclination correction factor, we do take into inclination correction. If it is ground sloping condition, then we talk about ground correction factor. If base is sloping, then base correction factor. And likewise, all that respect shape, if it is a different shape of the footing, then we do take into consideration of your shape correction factor and so on. So this is expression what we have for estimating your bearing capacity of the footing according to Hansen if the phi value of the soil is equal to 0. Okay. So with this, we'll stop our discussion for today and we'll continue our discussion in our next class. So in today's class, what we have talked about is according to Terzaghi's theory or Mayerhof's theory or Hansen's theory, how do we go on to estimate the bearing capacity of your footing is what we have understood. In our next class, we'll try to discuss about how to estimate the bearing capacity of your footing, taking into consideration of your Wessex theory or taking into consideration of your Indian standard code specifications, because Indian standard code also specifies the criteria on which how the bearing capacity of the footing is to be estimated. So we'll try to look at those, because we will not be able to cover all the aspects of different theories. Just to give you an idea, we are trying to talk about some of those very popular theories what are commonly used or widely used in estimating the bearing capacity of your footing. Okay, thank you all.